The next type of reaction we're going to be covering in this unit is single replacement reactions. These are very similar to double replacement, but as you can see from the general format below, it doesn't have two compounds, it only has one. We will kind of be looking at the rules that will influence single replacement reactions. There are two separate types, so we are starting with cation replacement in this video, which will be the majority of the type that we look at. So in cation replacement, as it is sort of inferred, we will have the replacement instead of both things of just the positive charge in the compound. So in general, a single replacement reaction is when one element replaces another in a compound. Specifically for this type of cation replacement, we're saying when the cation replaces the other cation in the compound. So A and C are going to switch and make a new formula. The difference with this one compared to our other reaction types is that we will be referencing something called the reactivity series. And this means that the reaction will only happen if C is more reactive than B, meaning it is more aggressive and a better partner to B than A. And so a general way of thinking about this is that the more reactive thing always wants to be in the compound. So if the more reactive thing starts in the compound, nothing will change. However, if the more reactive thing is alone, then it will replace the other thing in the compound, so it gets to be in the compound. So when we're looking at this, some of the same rules apply as when we are making new formulas. So elements should not have any subscripts on them unless we have hydrogen as one of our things being replaced. So in general, elements, and I'm talking just elements, not polyatomic ions, should not have any subscripts when you move them over. This is because, like before, we want to be making a new formula based on their charges. So again, unless we have a polyatomic ion for B, there should be no subscripts that transfer over. The other small thing to note here, and this will come up more in our other type, is that if A is hydrogen, we will need to Hoberfinkel or add the two because it's diatomic. So that will not come up that often, but if we have an acid and the H is getting replaced, when the element ends up alone, it will need that two because it is diatomic. So let's go and look. We have our first example here. We have copper, we have chlorine, and we have sodium. So in this case, copper is a +2, sodium is always +1, and chlorine is -1. Our first thing that we should be checking is, will they even switch? So looking here, we see we have copper all the way down here, and then we have sodium here. The farther left on the series, as you can see, is more reactive. So in this problem, and in general, sodium is more reactive than copper, meaning it needs to be the thing that ends up in the compound. Because sodium is currently alone, not in the compound, it will swap so it gets to be the thing in the compound. Meaning Na with its +1 charge and Cl with its -1 charge will end up together, and copper will get kicked out and be alone. Now in this case, because copper is not bonding with anything, the charge doesn't really matter. This is called what is reduction. So the charge goes from 2 to 0, meaning it becomes just metallic carbon, not ion carbon. So we want to make the correct formula here. We see Na and Cl both have a 1 charge. So this should just be NaCl. This 2 here does not move, so this would be incorrect because sodium does not have a 2 charge, so there's no reason to put a 2 there. And then you would go ahead like we have been doing and balance. So copper has 1 and 1, sodium has 1 and 1, but chlorine has 2 and 1. So that means I need to put a 2 here, which will change both of those to 2, and that means sodium will also need a 2. That is generally how it works. It's very similar in a lot of the processes to double replacement, the difference being that we have a single element that ends up by itself, and we're only making one new compound, and that we need to reference the activity series. Below, I have some examples. It is up to you if you want to continue to watch and go through them, but I'm going to go through them now. If you want to try them on your own, feel free before I give the answers. So feel free for these first two. If you want to pause, I'll do 2 at a time here. Pause the video and attempt these if you would like. Okay, like always, our first step in single replacement is to decide, will they even switch? Because if not, then I don't have to do anything. So sodium is more reactive than silver, and because sodium is alone and not in the compound, it needs to change that situation and it will end up switching. So these two will swap. So Ag ends up alone, sodium ends up then with hydroxide. Now, again, because it ends up alone for silver, we do not need to care about its charge anymore because it's just by itself. And then Na and OH will make a compound. They're both a 1 charge. This will already be balanced, so we do not need to do anything extra there. Okay, next example, we have calcium and we have copper. So here's copper, here's calcium. Calcium being alone and more reactive also means it needs to switch because the more reactive one should end up at the end in the compound. So I'm going to go ahead and swap those. This is a +2 charge. This is -2. Calcium is always +2. So our formula is going to look fairly similar here. Calcium ends up, not calcium, copper ends up alone. And calcium ends up with sulfate. Both of those have a 2 charge. So our formulas look pretty much the same. This also ends up as balanced. Okay, next 2 examples. Again, feel free to pause if you would like to try on your own before I go over the answers. Okay, we need to just pop back up to our reactivity series here. We see, in this case, we have hydrogen, which is included on our activity series, even though it's technically not a metal. And then we have iron. Iron is more reactive than hydrogen. So iron is already in the compound, which means the more reactive thing is already in the compound. Hydrogen will not be able to kick iron out of that because iron is a better attractor of carbonate. And so hydrogen cannot basically steal carbonate from it because it's less attractive to it. So simply put, no reaction. If they can't switch, nothing will change. No reaction will occur. Okay, the next one is we have sodium and iron. So I'm going to go ahead and just check those against each other. Sodium is more reactive. So going back down, we see sodium is alone, which means it will end up switching. Iron now ends up alone. We don't care about the charge of iron because, again, it is by itself, not with anything else. Sodium is +1. And bromine is also a 1 charge. Notice, again, I did not move this 3 because that 3 came from iron. And now that it's not with iron, it's with sodium. Sodium gives it a 1. So that is going to be the difference there. We do need to balance it because of the fact that we changed the amount of bromines. So I'm going to put a 3 in front here. So we have 3 bromines again, which will also mean I need a 3 in front of sodium. In general, I would say for most single replacements, they're fairly straightforward to balance since you do have 2 elements that are just completely by themselves. Usually, if you do need like in the case of the bromines, to balance that out, you can just put whatever number you need then that changes, in this case 3, in front of the single element. But that is cation single replacement.